Yeah, let's take a look at this differential equation. We're going to use Laplace transforms to solve it, and I wrote a few of the properties here. The Laplace of the second derivative um, of some function. Remember, x is not just a variable, it's a function of t. We often won't write that just to save a little bit of um, redundancy, I suppose. And then we have the Laplace of the first derivative of function of x, the function x of t. And last we have this t multiplier, and there's that formula. Looking at the problem provided, we only have t as to the first power, right? So really we could just look at this one when n equals 1, because we only have, again, a t, right? T to the first. Laplace of t x of t equals -1 to the 1, so -1, and then f prime, so negative f prime of s. Right, that's really the only one we need for this example, so we'll just use that form. Okay, let's start it out. So we are applying Laplace, right? Laplace is an integral, and integrals can go across addition and subtraction. So we are taking Laplace of both sides of this function. To save a little bit of writing, I suppose, let's look at it as, like, I'm just gonna think of distributing, right? We're taking the Laplace of everything. So the Laplace of tx double prime. Then we have a minus 4t, so minus, remember with Laplace, the linearity, right? That's where we could separate the plus and minus of each term, and we can remove any constant coefficients. So I'm going to go ahead and do that now. Minus 4 times the Laplace of tx prime. And then we have minus x prime, so minus the Laplace of x prime. Okay, and then we have plus 4tx, so plus 4 Laplace tx. And then we have plus 2x, right? I'm looking here last. So plus 2 Laplace of x. And of course we have Laplace of 0. Laplace of 0 is just 0. Okay, so now we need to apply the Laplace transforms on each term here. Laplace tx double prime. So we have this for the Laplace of x double prime, but because of the t, we need to do this to it as well. Negative f prime of s. All right, so how does that look? It's going to look like we have negative, and then I'm going to go ahead and write the Laplace of x double prime. We had s squared x of s minus, the last two terms are going to be 0. I'm going to write it as a placeholder, right? But in this problem, very convenient that both of those terms are 0, right? And this one as well. So minus s times 0, again, I'm writing it to show I did in fact use the formula for Laplace of the second derivative, but it's negative and then f prime. So I need to remember to do derivative. I'm going to use this notation. Remember, it's with respect to s, right? So d ds as we move forward. Okay, So that is this piece. I don't want to get too colorful here. I'll stick with purple for another term. So next we're going to do this, so minus 4. Laplace of x prime is given right here, but we have a t, so we need to make it negative and do derivative. So this negative 4 turns positive, negative 4. S, x, s, s, x, s, minus x of 0. So again, we know that that term is 0, so minus 0. Derivative, right? It had a t. All right, we'll do 2 lines. So that is this piece here. Pick a new color. Next we'll do minus Laplace x prime. So minus Laplace x prime we have written s x of s minus x of 0. Again, that is 0. Okay. Plus 4 Laplace tx. So now we'll do this piece. Plus 4. Okay, Laplace of x is just x of s. But we have the t. Right, so Laplace of, excuse me. Laplace of s, sorry. So we have the t, we need it negative, and f prime, right? So x of s prime. Sorry, I was drawing a blank there for a second. My mind went astray. Okay, 4 Laplace t of x. So we do the Laplace of the function x, which is just x of s, but the t created a negative, and we need x prime. Okay. Oh, one more color in here, I suppose. Okay, we have 2 Laplace of x. So plus 2 x of s. And all of that equals 0. Okay. Let's simplify this, collect some like terms. So we need derivative. Now remember, I have a bunch of zeros in here, right, for these t's. I don't need that, I don't need that, I don't need either of those. So I'm looking at this term here only. I need to do derivative with respect to s. That requires product rule because I have s squared multiplied by some Laplace of s, right? Of that function, Laplace of x of s. So we have 2s x of s. Now we have a negative up front, so I'm going to go ahead and just distribute that now. And then minus, again, the negative out front, s squared x prime. Okay, f prime g plus f g prime. All right, plus 4, now go to the next term. Here. All right, I need derivative, so again, product rule, f prime g plus f g prime, so plus the 4 as well. Derivative of s1, so 4 x of s plus 4 s x prime. Okay, So that was that next term. That was the first one. The rest, I think, right, pretty straightforward. We have a negative sxs, negative s x of s, and then negative 4x prime, negative 4x prime. We didn't need product rule there because we just had one function derivative, plus 2x of s equals 0. All right, let's group. We want all the derivative terms first, I suppose. So we have this one, and that one. Okay, grouping all those, we have an x prime of s. We have negative s squared plus 4s minus 4. Okay, let's change the highlighter color. Okay, grouping all our xs's. We have this one, this one, this one, this one. All right, can we combine any of them? Yes, we have a negative 2s and a negative s, so we have negative 3s, and then we have plus 4, plus 2, so plus 6. All right, at first it kind of looks like I don't know what to do next, but this actually becomes a separable differential equation, right? We have a derivative and the normal function. So what we're going to try to do is group all those functions on one side and the rest on the other. So I don't know. I guess let's move this stuff to the other side of the equal, right? We'll just add that to the other side of the equation. So we'd have negative 3s plus 6 x of s equals, I'm going to flip all those signs, s squared minus 4s plus 4 x prime of s. All right, let's divide by the x of s and then on both sides and divide this thing out. Okay, rearranging terms, we have x prime of s over x of s equals negative 3s plus 6 over s squared minus 4s plus 4. Hopefully all my arithmetic checks out up to this point. Okay, we should be able to simplify first. So if we factor the numerator, we have negative 3s minus 2. Denominator, we have, what, s minus 2 squared. Perfect. So reducing that, we have negative 3 over s minus 2 equals x prime over plus of x of s. All right, we want to integrate because both sides we have du over u, and we know the integral as ln u. Now, it is absolute value, but because of the domain restrictions, it wouldn't matter. Oftentimes, we assume that's going to be positive anyways. So we're integrating with respect to s. So this right-hand side, we have ln x of s, right, du over u. Left-hand side, we have negative 3 ln s minus 2, right? We have, look at the ds over s minus 2, that's ln s minus 2. Can't forget the plus c. I ran out of room. I kind of forgot it there for a second, but we do have the constant, right? Okay, from here, it's back to elementary differential equations. ln s minus 2 to the negative 3 plus c equals ln x of s. So we both sides. So remember, all of this is the exponent, but that's okay because e plus c, we could think of this instead as e to the c. I'm going to do this off to the side, save a little bit of room. Okay, this is old stuff, but e to the c times e to the ln s minus 2 to the negative 3. Right, and that's why we could still cancel that ELN, and we often just call this e to the c some new constant c. Okay, so we have c, s minus 2, negative 3 equals x of s. Now we can do the Laplace inverse on both sides, and before we did that, we'd probably think of this piece here as this. Okay, well, we have a c in the numerator, right? So when we Laplace inverse, we could find this on the table, and therefore x of t is c, and then the formula, we get t squared e to the 2t, e to the, 2t, because that formula came from, I'll go ahead and write it really quick. The function x of t or f of t, most books use f of t, is tn e to the at. But the Laplace, the transform f of s, is n factorial over s minus a to the n plus 1. Okay, so n plus 1, that tells me n is 2, right? And then s minus 2, so that told me a is 2. Why did I not worry about n factorial? Well, because we have a constant, an unknown constant, right? So if you multiply that by 2 factorial, it's still some constant that I don't know. So kind of irrelevant, right? I don't need to say 2 times the constant. Oftentimes, like, I guess I should change variables, right? We should maybe had called the constant above a, let's say, right? So this constant was a, and why is that important? Because this c is not the same constant as above, right? It's a new constant. Or we could have done some subscripts with c1, c2, and so forth. Regardless, like that discrepancy, right? There is our original function that solves that differential equations given the initial conditions. A lot of work there. Whew.